Hello and finally welcome back after a 5-year break. I'm sorry about that. And turns out to be quite complicated actually to solve the problem which I left you with in the last episode, which was the fact that this Hello World program, we managed to write the Hello World on the screen, but then we didn't manage to exit the program and get back into the DOS prompt. So that was pretty complicated to solve. Then at some point I got distracted and other things happened. But anyway, I'm back today and I hope to be able to solve this problem now finally, so that we can actually continue understanding the lower level programming in assembly of this IBM Personal Computer 5150. So as I said, this is our assembler program here. And we actually discovered what to do by reading the DOS manual. And so we had tried out this function 9 here in DOS, here it is, to print out a string, which we managed to do, but that's all we did. And so after this, there's nothing further in our program, and the program doesn't exit automatically. So in higher level languages, you would expect the program to end when you reach the end of all of the statements, but of course in assembly that doesn't happen. We need to do something explicitly to exit the program. And a first clue to that was given when we read through these different DOS functions, which we accessed using this software interrupt, which some other processors call traps, which is located in interrupt vector 21 hexadecimal. And there's this function 0 here called program terminate. So it resets a number of other interrupt vectors. It clears any files which the program might have opened, and then it transfers control to the terminate address, whatever that is. It also restores values in the program segment prefix. So this is something which is, for the moment, still mysterious to our programmer from 1981. But then we get this note here, which is pretty disconcerting. It says this call performs exactly the same function as software interrupt 20 hexadecimal. So apparently we can do the same thing by, instead of calling 21 hexadecimal with AH set to 0, that's the same thing as calling 20 hexadecimal. But it is the program's responsibility to ensure that the CS, the code segment register, contains the segment address of its program segment prefix control block prior to calling this function. And so we need to set the CS register to something which is the program segment prefix, but we don't really know what that is. And so probably some more reading is needed in order to understand fully what's happening here. Now it turns out that there is a section E, this is Appendix D, is the listing of all the DOS commands, but Appendix E gives us a better overview of what happens when DOS actually loads and starts a program. So the first bit here is just an explanation of how DOS organizes the memory in the IBM Personal Computer. But then here we come to the program segment, an explanation. So command.com is the program that DOS starts, which gives us this command prompt and allows us to type commands. And so it's in fact command.com which starts executing other programs. When we produce our hello.exe file, it's actually up to command.com to load that into memory and to start running it. And so here's an explanation of how that works. And so at offset 0, so first of all, DOS or command.com looks for a piece of free memory, and it calls this area a program segment. So it makes sure that it starts on a segment boundary, that is a 16-byte aligned address, and it sets a segment register. And at offset 0 in that segment, there is something called the program segment prefix, which is this thing we need to point to if we want to exit our program. Okay, it then loads the program at offset 100, so that's 256 bytes below the beginning of this program segment. But it has a note here that exe files might be loaded somewhere else. So this 100 hex is not fixed. But there is this program segment prefix, which DOS creates somewhere in memory. And the program returns to command. So how the program exits by jumping to offset 0 in the program segment prefix. And then by issuing an int 20. So this is all, or by issuing an int 21. So these two techniques we read about earlier. Apparently these are things we could do, or we can jump to offset 0 in the program segment prefix. And that's a very interesting statement, because that implies that this program segment prefix, whatever it contains, at offset 0 is executable, runnable code, machine language code, which we can jump to. And it says here the instruction int 20 is the first item in the control block. So apparently if we jump to address 0 in this program segment prefix, it'll automatically execute an int 20, which will actually exit the program. And that is, of course, doubly interesting, because if we do a jump where we specify a segment address and an offset address for our target for our jump instruction, and we set that segment address to be the program segment prefix, then we'll automatically have fulfilled this condition to set the CS register to point at the program segment prefix. And in fact, as far as I can tell, it's the only way you can set the CS register to the program segment prefix, because the CS register and the IP register, those are the registers which the 8088 processor uses to fetch the next instruction. As soon as you set a value in the code segment register, the next instruction that the 8088 will run will be located in that segment. There's no way around that. So this is a very harsh statement here to say that it's the program's responsibility to write to the code segment register. In fact, whoever wrote DOS, in my opinion, kind of goofed up things here a little bit, because that's extremely hard to do. You can't simply set the CS register. The 8088's instruction set doesn't actually allow it. You have to jump. It's the only way you can change the value of the code segment or the instruction pointer. So there's no way your program can issue an interrupt 20 or an interrupt 21 if it's not inside this program segment prefix. But the program segment prefix is not something that we write. It's something that DOS, the command.com program, creates when it starts running a program. So in effect, I think jumping to this offset in the program segment prefix is the only way to exit a DOS program. In fact, this whole stuff was so complicated that in later versions of DOS there is actually a much better way of exiting a program. There is a new function call which you can call, which doesn't depend on the value of any of the registers. You simply call that interrupt and it will exit the program. And that's the way later versions of DOS expect you to exit programs. But so in this initial version, really the only thing we can do is to jump to this offset. So okay, the way we need to do that is we need to figure out where DOS creates the program segment prefix. And that is entirely up to DOS's discretion. That's not something that we know while we are writing the program. That's something that DOS decides based on whatever else is in memory at the time when we decide to run our program. So there must be some way of figuring out how that works. And the clue is actually found a little bit later here. It says, so this explains what happens when you start a program, and in particular for exe programs, which is what we have, it says that the DS and ES registers are set to point to the program segment prefix. So notice that in our program, when we start running, we actually overwrite the DS segment immediately with our data segment, because we actually need that for this interrupt to start writing our hello world on the screen. And so we're actually overwriting this information which we get from DOS, which is the location of the program segment prefix. And we shouldn't do that. We should save the value of that register before overwriting it with this information here, so that we can safely jump to it. So that's probably what we should try and do. So now here my computer's obviously hanged, so I need to hard reset it. That's the only way you were able to work with the IBM PC back then. So here we go, it's going to reboot DOS. So we're still on 1st of August 1981. Let's go back to our B drive and let's try and save this DS register at the beginning of the program. So let's go into Edlin and edit our program. Here we are. And so before we actually move this segment address into DS, let's insert some code here to to actually save the value of the DS register. So we'll do a move into we'll call it a memory location. We'll call this seg of the program segment prefix, and we'll save the register DS in there. Okay, so that's fine. But of course we need to create something in our data segment where we're going to actually store this value of the program segment prefix. Okay, so let's do that. 10, or let's put it behind this hello world screen. So let's do an insert at line 12 and create this variable seg PSP, and we'll call that, so that needs to be a word because a segment is 16 bits long. And we don't actually know what it is. We're actually going to write something there, so when we start the program, the DOS doesn't need to put any specific value in there. Okay, and that's that. So now let's have a look at our program. So now we have a bit of memory where we're actually going to store whatever DOS gave us as the segment for the program segment prefix. Then we do what our program should do, which is to get this message and print it out on the screen. And then here, in line 8, we need an instruction to jump to offset 0 in this segment. So that's something we need to do now. And to do that, we need to issue a jump instruction. But then we actually need to tell the assembler that this has to be a jump to a specific segment and a specific offset. And so there's a very specific syntax to do that. And we can find out all about that in the manual for the assembler, specifically the jump instruction, which I have here. And so what we are interested in is something called an inter-segment. So we're jumping from one segment to another. The program starts in our code segment, which is not the program segment prefix. That is somewhere else in memory. DOS gave us a code segment which is potentially in a totally different location. It could be this 100 bytes beyond the program segment prefix, but it doesn't have to be for exe files. So we shouldn't assume that it is. Let's just assume they're completely different regions of memory. And so we need to figure out how to code an inter-segment jump using the syntax of this assembler. Now this is a direct jump. So this would be true if we knew the segment of the program segment prefix. Then we could hardcode it. I don't know, maybe it was 4CA, something like that, hexadecimal, and then that would be the segment and that would be the offset. But that's not the case. We don't know at compile time or at assembly time what this segment address is. We need a dynamic variable. We have it actually here in memory. So we need an indirect inter-segment jump, which is written in this way. And so what we need to do is a jump, and then we need to make sure that it's a double word pointer, and then we need the effective address that we want to jump to. Notice that this effective address, this is a location in memory, and this location, it needs to have, I'm imagining that dest here means the offset of the address, and this is the segment of the address. So we need 4 consecutive bytes in memory, of which the first 2 are the offset and the next 2 are the segment. And that's the only way we can do this. So, okay, what we'll actually need to do is in our data segment, we have a location here with the segment address, but we also need the offset in that same location, and then we can do a jump d word pointer to the offset of the program segment prefix. And if we make sure that that is located just in front of the segment program segment prefix, then we should be in business. So that's the last thing we still need to do, which is in our data segment here, we need another value just before the segment address we want to jump to, and that will be the offset of the program segment prefix. That is also a word, and that we know is 0, because the manual told us we need to jump to offset 0 in the program segment prefix, and DOS promised us that there would be this instruction there. Okay, so we've inserted that. Now let's have a look at our program. So we save the DS register, then we do what we used to do, and then we jump to this offset, and we do a far jump, which is at offset 0, and then this segment address which we're attempting to save. Okay, that looks good. So let's save that and try and assemble it. So we call the macro assembler and we run it on, or actually the macro assembler will ask us for our program, which is hello. So let's write that here. We'll have that object file. We'll do a listing file in case we have errors which we don't understand, and let him chew on that for a while. And then we get 2 errors which are can't reach with a segment register. Yes, okay, indeed. Let's have a look at this program again. Hello.asm, because we're actually doing something without realizing it that the assembler doesn't know how to handle. Here we are telling the processor, I would like you to write the contents of the DS register in this memory location. But this memory location, seg.psp, this is going to be whatever the length of that string is, maybe 10 plus 12 plus, this is going to be the number 14. That's the offset in the data segment. But that's not enough for the processor to know where to write the data. It also needs the segment address of this memory location where it's supposed to write the contents of the data segment. So it's kind of a catch-22. We need to actually set this segment address first in the DS register so that the processor can actually write to it, but then we want him to write the contents of the DS register. Well, one way to do it would be to save the DS register in some different register, and then move that into this location. So let's try that. Let's delete line 2 as it, or actually replace line 2 as it is now, and instead of writing it directly into memory, let's first of all save what's in the DS register into the AX register. Now we are free to actually set the DS register correctly, and we're setting it to the segment of message, and that's the same as the segment of PSP because they're both in the data segment. In fact, I can make that instruction clearer, that's instruction 3, by simply saying move into DX the value of data. Let's have a look at that. So that's this, whatever segment this is. And the linker is actually going to write the address, or no, not the linker, DOS is going to relocate that and actually write the correct address in there. Okay, that's that. Then we write the DS in there. We write the, and this is a little bit too early, so we should insert code here in between lines, or in between 4 and 5, to actually save what we put in AX, which was the value that the DS register contained, the value of the segment of the program segment prefix at the beginning of the program. And so we now want that to go into our variable seg.psp, and we'll write AX into there. Now what does that look like? And now we write that in there, and then we have the program as we had it before, and then at the end we do this jump. Okay, so that should be a little bit better. Now we've set up the DS register so that these kinds of offsets, these kinds of memory operations, our processor is actually able to perform them because we have the data segment set up. Okay, that's good. Let's try that. So we're gonna call our macro assembler again on the file hello. Yes, let's do a listing and see what it says this time. Same error message. We still can't reach. We can't reach with a segment register. Okay, well, as it turns out, I happen to know what this error is because I looked into it before. And if you read the assembly, the macro assembler manual very carefully, and there are 400 pages of it, so it's a lot of reading you need to do. But at some point, you'll probably have read that. And so I think what our programmer would then discover is that although we have told the CPU, the 8088, which segment he should use when accessing memory, we haven't told the assembler. The the assembler isn't clever enough to realize that the DS register points at the data segment. And when we write move into seg_PSP, as far as the assembler is concerned, is some address inside the data segment. But it doesn't know which register it should use. It should tell the CPU to use in order to read this seg_PSP. We actually need to tell the assembler that. And that's done with a directive, which we should do here in line 5, because in line 4 we actually set the DS register to point to the data segment, but we haven't told the assembler. So we need to do that, and this is with a so-called assume statement, one of the more confusing aspects of assembly programming on a segmented architecture like this one. So let's just write it. We need to assume, and let's do it completely. So we can tell the assembler it can assume that the CS register will point at the code segment, which is true, except for this last jump instruction. We can tell him that the DS register will point at the data segment, and while we're at it, we can tell him that the SS register is pointing at the stack. And let's assume nothing about ES. ES will actually contain the program segment prefix, and that is completely meaningless to the assembler because it doesn't know about that. This is a DOS concept and has to do with the execution. So there's this special syntax where we can say, okay, you assembler, you should assume nothing about the ES register. Just don't use it. Okay, and so doing that, it should now be able to resolve this and realize, I can actually find out where seg_PSP is. I can also find out where off_PSP is. Both of those are in the data segment, and it can use the DS register to tell the CPU where to fetch that information from memory. So there are 2 steps. You need to tell the CPU and you need to tell the assembler. That's life in assembly programming on the IBM PC. All right, let's try that. So macro assembler again, and we want our file hello. And do one less thing. There we go. So what does that do? And what do you know? We've solved the error. The next question is whether it works. So first of all, let's link this program. And let's link it into hello.exe. And let's do a linker listing file as well, no libraries, and all of these other defaults are fine. And let's see what the linker thinks about our program. Okay, that seems to run. So the big question is, will our jump to address 0 in the program segment prefix, will that work, and will we actually get control back into DOS? And hey, that appears to have worked. Okay, so that's good. That is, now we actually have a working Hello World program in assembler, and that took quite a lot of doing. We needed to know about DOS, we needed to know about the program segment prefix, we needed to know about far jumps, we needed to know about segment registers that the assembler can assume. This is complicated stuff, and I keep wondering how intuitive that would have been to a programmer at the beginning of 1981. Remember, this CPU was brand new in 1981, maybe 1 or 2 years old. Not many people would have had experience with it. Yeah, but anyway, we've managed to do it, and the information is in the manuals, even if it's scattered around. And so, just to remind ourselves, this is what we needed to do. So we needed to, first of all, save the DS register. So we did that by moving it into the AX register. Something else we could have done is to push it on the stack, because the stack would have been set up by DOS. We just use the register. Then we actually set the DS register to point to our segment in our program. So that's no longer pointing at the program segment prefix, but that's okay because we saved the value. We hard coded the 0 address in there. And here we then just start running our program. And at the end of the program, because we saved these values, we then do an indirect jump. A far jump, this D word PTR means it's doing a far jump. It's getting both the offset and the segment. And this will ensure that it jumps into this first byte of the program segment prefix, which allegedly, according to the manual, contains an int 20 and will return control to the command interpreter. And in fact, that worked. And a good way to see this, to actually, because sooner or later you're going to have to debug programs when you're working in DOS, there is a debugger which comes with DOS. So in the DOS manual, which is here, there is an entire chapter on the debug program, which is actually, turns out, a very useful program. And here it is. And so I think we've used it before just to look at memory, but you can also tell debug to load some executable. And so I'm going to tell him to load this exe. Yes, of course, because I have the debug, actually, it's a DOS command, so in theory you would need a DOS diskette, but I've actually copied it onto my assembler diskette. I'll just show you everything I have on this assembler diskette. So we have the assembler itself and the linker, but then I also copied, so the command interpreter means that whenever the linker exits, I don't need to insert the DOS disk. And then I also have the debugger and edlin, which are commands which I constantly need while developing assembly programs. So we need to prefix this with A, and then we can run the debug program on our executable. And there we go. So we can have a look at all the registers at the beginning. And this, as it turns out, this is the first instruction in our program. So let's just disassemble. Notice the CS register is pointing here at segment 4AF, and the instruction pointer is at address 0. So let's just have a look what that is. So we can, I don't think that works, no, but you can do CS0. This is our program, yeah. And remember, I said the DOS would actually insert the correct address for the data segment, which apparently it's done. So 4B1 should be our data segment, and we can confirm that by just dumping the contents. So the first thing we should see is our message, indeed. And then behind our message, which ends with $, it turns out that we actually have 4 more bytes, which will then later contain this segment address. And we can actually see that happening by running our debugger. But something else I wanted to point out is that the DS and the ES registers, they're pointing at 49F, which is something different. It's not the code segment and it's not the data segment. It is the program segment prefix. So let's have a look at that. So according to this DOS manual, this is something that DOS creates, or the command interpreter creates, whenever it loads an exe file for execution. And address 0 contains these bytes CD20. That ought to be interrupt 20 if we are to believe the manual. So let's confirm that by disassembling that. And indeed, there is an int 20 right there in the program segment prefix. And so when we jump there, the code segment will be 49F, because that's what our program ensures. So let's just see that in action. So there's a trace command in this debugger, and that simply runs the first instruction. The first instruction was to save the DS into AX, and DS is this program segment prefix. It's this address where our int20 is, and we save that because in the next step we're actually going to take the DX register. I see, it's actually, so this debugger, yeah, we went one step further. Yeah, so we actually moved the 4B1, which is the data segment where DOS placed our data, and that's now in the register DX. Here it is. And so now we're moving that into the DS register, and that's going to overwrite this address of the program segment, but we moved that into the AX register first. So now this is the program segment prefix. This is our data segment. So now if we do dump DS0, we'll actually get our data segment. Our code segment hasn't changed, and this is now the next instruction, and it says move into DX the value of 0. Why are we moving 0 into DX? So I fear, let's do a disassemble again of our program. So we did that. The debugger is, sometimes it just jumps over a statement. So apparently it's completely jumped over this statement, which was to write the contents of AX at memory location 12. And so if we look again at our DS register, if we look very carefully, we'll see that this second byte, this is in the little endian encoding. So in the usual way of reading that would be 49F. That is indeed the location of the program segment prefix. So that has been written by this instruction, which our tracer just jumped over without warning us. And so now we're here at dx move into dx0. Now this 0 is just the offset in our data segment of the message, and that happens to be 0. Okay, so that's the next thing it's going to do. It's done it, and the next thing after that is to move put the value 9 in there, and that's going to call this DOS routine. So we'll do that, and then that's going to call the DOS routine, and that will actually write hello world. So this was the call into DOS. And now, again, our debugger has apparently jumped over the next statement. Let's have another look. If we look, what our program was. So our program, after we did, yes, because, so our code segment now actually points in the program segment prefix. So I think it was for AF, that was our program, that's correct. So it did that, and then it also did this long jump. So this is this L, the long jump. The segment address, no, this is the memory address. So to find out where it's going to jump, we need to look at the 4 bytes which are located. Probably DS is still valid, so we can look at that address, but that's just going to be the offset and the segment. Here they are, the offset and the segment of the program segment prefix. And so what's located in there is indeed this int20 instruction, which is the next thing our program is going to execute. I don't know if that's going to get me into DOS. No, it tells me the program terminated normally. So yeah, there we can see how this stuff works, and we've actually confirmed that this program segment prefix does indeed contain the 2 first bytes in that program segment prefix is something you can jump to. So that gives you a little overview of this debugger, which I assume would have been very useful to someone in 1981 to understand what is actually going on here. All right, now to conclude, I would still say this is a pretty convoluted way of exiting a program. And I'm not convinced that that is the standard way. I mean, there are obviously lots of programs which the developers at Microsoft and at IBM wrote for the IBM PC, and so they must have solved this problem somehow. And so it's interesting to look at some example programs provided by IBM at that time. And so, in fact, the macro assembler comes with a few sample programs. So we can look at those to see how they actually solve this problem of writing into the code segment register in order to be able to exit a program. So let's find the assembler. Here it is. So let's list the contents of A, and there is an example program here. This exm1s is a good one. So let's copy that onto our diskette, 1s.asm2b, so we can look at it. exm1s.asm. No, that's not right. That shouldn't be a new file. Yes, I want to abort. It didn't copy. Yes, of course, because we need to get it from the A drive. xmp1s.asm to B. Here we go. One file copied, that's better. And now we can look at it. xmp1s.asm. And here it is. Okay, so lots and lots of comments. This is very reminiscent of the COBOL experience, which I had a few episodes ago. Apparently, the engineers at IBM also write their assembly program in the same style. So lots and lots of descriptions. The only real substantive thing here is a definition of the stack segment. That's it. That's all there is on this page. So let's look a bit further. There is a data segment, which they call work area. It sounds an awful lot like COBOL again. But we're interested in this code segment. And so here's something new. This says start proc var. Just remember that for a moment. But then the interesting part are these comments here. So these are comments, and it tells us that at entry, CS will point to the address of the entry point, which presumably is here. And that's correct. That's what we saw as well when we looked at our program in the debugger. The instruction pointer will be 0. The stack segment will be set to the stack. So that's all fine. We actually knew that. Then here it says DS starts is the segment address of the program segment prefix, and that we also discovered. In fact, ES points to the same area. When the program exits, it is the user's responsibility to ensure that the code segment is the segment address of this program segment prefix, which is in the DS register when the program starts. Originally DS or ES. And so the way to do that, this program uses a different technique. It actually pushes the DS register onto the stack. It subsequently, this is a shortcut to, it says it here, clear the register. So you could also write move 0 into the AX register. But this is actually, the machine language for this instruction is a byte shorter. So this was a very early optimization. And then you push this 0 onto the stack. So on the stack are the program segment prefix, segment address, and the number 0. So that is actually the 4 bytes which form the long jump address of the exit code, this int20, which is in the program segment prefix. And so this program pushes it on the stack. And then if we look a bit further, so this is the main routine of whatever this example program does. This looks like a print message. So this is the same call that which we used in our hello program. Sorry, I didn't want to do that. I wanted to list what happens further down the program. There we go. We're not quite at the end yet, almost there. And here, for the return to execute properly, the stack must be restored. So it uses a return instruction. And it uses a return instruction, which, as we remember from building our own CPU, the way return is implemented is when you call a function, that is actually supposed to put the return address on the stack and then jump to the function. But we tricked the return instruction, we essentially tricked the processor by pushing some address on the stack ourselves. And the address that we pushed on the stack happens to be the 0 byte in the program segment prefix. And that's the trick that this program uses to do this jump to the beginning of the program segment prefix. So rather than saving it in a variable in memory, it actually pushes it on the stack and then uses a return instruction which will indirectly perform that jump. And that's actually shorter because the return instruction is just one instruction, where we had to do this memory management and have this very long jump with very explicit addresses. It's actually shorter code, but it's a bit more convoluted to understand. And the final thing which is important is for this return instruction to actually do a long jump, so a jump to a different segment register. It is extremely important that the procedure, that we define this procedure as a far procedure. It is this assembler directive, which will ensure that that return instruction becomes a long return instruction. So, a lot of new things, but it's very instructive to look at this example. And I imagine someone in 1981 would have done that, would have looked at these examples and realized, this is actually how you do it. So I think as a final iteration on our hello program, we should try that. So let's see if we can change our hello program to use that technique and see if it looks any shorter. So we go back to our hello.assembler. Okay, here's the program. And so instead of moving that into the AX register, what we actually want to do is push it on the stack. So we'll push DS on the stack. Okay, the next thing we want to do, so this is actually our program. So we also need to push this offset 0 on the stack. So we need some code before line 3. And we can do the same that this other program did. So we can put it in the AX register and then push that on the stack. And that way we will actually have the segment and the offset of the return address on the stack. And then we get our program. And that does what we need it to do. And then instead of this jump, what we need is a return instruction. So that's line 12. Now it needs to become a return instruction. But there's one further thing we need to do. We need to tell the assembler what sort of a return instruction that is. So we need to tell the assembler whether this is a so-called near procedure, a procedure in the same segment, or if it's to be called from a different segment. So the assembler, like the code, assumes that this procedure is being called from somewhere else. It doesn't know that we're actually tricking the processor by pushing some fictitious caller address on the stack ourselves. But so in order to let the assembler know that this should be a file return, we need to do this procedure business. So we need some code, actually some directives in front here. So let's call it main, like we usually do in C. And that's going to be a var procedure. And then we also need to terminate that procedure, and so that we can do here in line 14. And we need another instruction there, which is main end procedure. And that's it. And so let's see what that did. So that now looks good. One final thing we could do. Our program started execution at address 0 in the code segment. And the way our program is right now, the first routine which we have is actually the entry point. But that need not necessarily be the case. There could be other procedures in there. Typically in C, you write your main function right at the end. And in these early assemblers, that's probably a good idea as well, because it doesn't know where functions are which come later in the source code. And so the assembler had a way to do that. You can actually give a start address which gets written into the exe file, and DOS reads that and sets the code segment, the instruction pointer, correctly. You can do that with this end statement on line 26. So we can modify that to tell it exactly where the beginning, where the entry point of our program is, and that's good practice. That's also something which you could see in the example program. Okay, so now let's have a final look at our program. This is our only procedure, and it is var. We push ds, which contains the program segment prefix. We push it 0. Then we get the data segment address, which is actually the segment of we really want. We can get rid of these variables. We don't need those. 19 and 20, so they are no longer of any use to us. So our data segment once again contains only the hello world. And then we do our interrupt to print the screen, and then hopefully we do a var return. That looks good. So let's try that out. There we go. So, and that is hello asm. Indeed, and we'll have an hello object, and we'll have a listing, and we will see what happens. And we have two problems. We have three problems. So first of all, we have an undefined symbol. We still have a reference to this seg.psp, which we got rid of. But then we get this really weird error, phase error between passes. So let's solve these one at a time. Firstly, we need DOS back. So we have the official assembler diskette in drive A, and that doesn't contain the command interpreter. So we should change that to our doctored version of the diskette, which does have it, so we don't have this problem in the future. And that is this diskette, so that it can actually load again. Then the second problem is we should solve this reference. I seem to have missed that, so let's get rid of it. Adlin hello.asm. So line 9 apparently. Yes, indeed. So we have that. Yeah, we did the save, so we can get rid of that. Need that anymore because we've pushed it on the stack, and we can forget about all we're interested in is this message. Now it turns out that with all these assumes and with these procedures, this trick which we used here of simply considering data to be some fixed value of the data segment, that doesn't really apply anymore. I spent a few hours trying to figure that out. You can't write it that way. So this instruction 6 is what's causing this pass compiler error, whatever it is. I imagine someone in 1981 would have also been frustrated and tried millions of things and looked at example programs and eventually discovered, okay, apparently I can't write that. And so the solution happens to be that we need to change that back to what it was, which is to explicitly write that it is the segment address of some variable. And in this case, there's only one variable in the data segment, so it has to be message. Don't ask me why. That's the way this macro assembler works. So as with any computer system, you'll have quirks and you'll find out about those sooner or later. But this ought to be it. So let's try again. Hello, that's the object file. We didn't do a listing. But if our program is error-free, then we don't care, and that has indeed solved the error, so let's link it. We'll take the hello object and make a hello exe out of it and do a map. And the libraries and all the defaults. And so this should still work, except that now we're using this technique of the var return, which we found from the example program. And indeed that works. So this is our definitive version of the hello program. And this is the source code. No, this is the source code. There we go. And so yeah, that now works. Okay, so maybe after a few days, our 1981 programmer could have had his first program to write hello world in DOS, as we've done now. And so, as I've done in previous iterations of programming languages, I've actually also gone ahead and wrote a version of the primes program in assembly. Now, of course, in my series on the homemade CPU, I actually did this assembly conversion already by hand. It was a different assembly language, but so if we look at this program, it's actually very simple, it's very similar to what we did back then, only it uses 8088 instructions. So this is obviously a lot more involved. We have this, we need to write things, and so writing involves this DOS function. I've written a fair amount of comments here to try and make it clear. Okay, so yeah, we can look at that. I'll just go through the entire program, and then you can pause the video and have a look at it if you want to understand more of the details. Yep, 47 list. Notice that all of these are near procedures, so they're meant to be called from within the code segment of the program. With the exception of start, which is this var procedure. And so here we have this technique, which we just had of pushing. So here I use XOR rather than sub, does the same thing, it makes this a 0. And that ensures that we can do the var return at the end, which seems to be the way this was done back in the day. And so let's look at the last bit of the program, and here we have our var return, and that's the end of the program. And also here, this start function is actually the last function in our code segment. So if we look here, there's a data segment, obviously in the stack segment, but then here we need to write this start, because if we don't, then the exe wouldn't start in our start procedure, would start one of the functions, and so that would obviously be completely wrong. And so in this case, this is actually mandatory. So let's try this program out. We don't want to edit it anymore. Sorry, we don't want to edit it anymore, so we do want to abort. Thank you. Let's try it out. So we try and assemble that. And it'll ask for the program name, which is primes. Yep, make an object file. Won't do a listing for now because I'm pretty sure this program is error-free because I spent some time on it before. Obviously, it takes a bit longer, but there we go. Now let's link it. And we have the object module as primes.object, which it should have written, and so let's make that a primes exe, sure, and no libraries, because we don't have any libraries in assembler, and we use the defaults. And so, if all went well, that should actually write out our prime numbers, and there they are. So, there we have it. We have made a simple hello program, which took a lot of work to figure out. The hardest part was actually exiting the program, which is a non-trivial thing you need to do. And so it turns out not the correct, but the standard way of doing that is with this var return from the main routine. And then we actually use all of those techniques, everything that we learned, and wrote our primes program in the same way. And so that happens to work as well. And so this is our, this concludes the start into the world of assembly programming for the IBM PC 5150 in 1981. And so my conclusion is that this would have been rough going, not impossible, but definitely rough going back in the day. But once you got started, this was probably the hardest thing to do. Once you know where to find the information, you can actually move pretty quickly. And so, yeah, as with all of these things. So that's a far cry from the first language which we looked at, which was BASIC, where we simply turned on the computer and we were in the environment immediately. And so that was called BASIC for a reason. But of course, if you look at the size of this primes program, this is 1 kilobyte large. I don't know if you remember the Pascal and the Fortran versions of these programs were 20, 30, 40 kilobytes large. So this is definitely the most efficient way, where it creates the leanest and fastest programs. And so if you wanted to get the most performance out of your machine, it was definitely a good idea to get into the world of assembly program. Now, there are basically two more things which we could look at in a future episode. There are two formats of executable files in DOS. If we look back at this explanation in Appendix E, which I think was here, it explains that there are two kinds of programs. There are exe programs, but there are also COM programs. For example, edlin is a COM program. That is also an executable program, but it works differently than an exe program. And so one thing we might want to do is to try and produce a COM program of our own, maybe a hello.com, which does the same thing, which produces hello world. And so that is possible, but it involves a bit more trickery. I think there are other tools which weren't immediately available to the general public. Obviously, IBM managed to produce edlin.com, or Microsoft managed to produce edlin.com, so it was definitely possible. It is also possible using nothing but the tools which they supply, which I will like to show you in some future video, but it's definitely more complicated than the official tools which produce exe files. But I think that's an important first step. The main concepts of assembly programming are definitely part of the development cycle which we've now completed. So yeah, sorry again for this long delay, but hopefully the next video, which might be the last, will appear with a little bit shorter delay. So see you next time.